So earlier we have discussed concepts of similarity transformations in the last class. Reduction of a matrix. So that means A is a given matrix. We want to transform into a diagonal matrix. And then we have seen P inverse AP is a diagonal matrix. If we can do either similarity transformation or if we use the model matrix, where T will have the eigenvalues of the given matrix A, and the diagonal elements of this D matrix will be the eigenvalues of the given matrix. Okay. Now today we want to see that orthogonal transformation. Okay. That means given a matrix A, we want to transform into a diagonal matrix, and by P we have to find P and P inverse. Okay. So here the transformation matrix, if it is a similarity matrix, okay, then we call it a similarity transformation. Now if P is orthogonal, then we call it a orthogonal transformation. So that's the idea of orthogonal transformation, orthogonal diagonalization. Okay. Now this orthogonal diagonalization is actually meant for, so for that we have to recall what is orthogonal matrix. So for orthogonal matrix, we know that A transpose A equals to I. That means here A transpose equals to, you can write A inverse. Okay. Now, given a matrix A, we take the row vectors, or we can take the column vectors, n by n matrix. So if you suppose x1, x2, and xn are the vectors of Rn, n-dimensional space, which are mutually orthogonal. And also, if we have and the norm, that is the length of the vectors, is actually 1 for all j, then the matrix, we call it a orthogonal matrix. So this row vectors, or you can say column vectors, they will be orthogonal to each other. Okay. Now if you take one example for this particular case, so if you take x1, the dot product x2, so if you want to verify whether two vectors are orthogonal or not, so what do? We have to take the dot product, and the dot product here is says 2 times minus 2, so this is minus 4, plus 0 times 5, so 0, plus, so this is 1 times 4, so 4, so this becomes 0. Similarly, x1 dot x3, so mutually they will be orthogonal, so 2 times 1, so this is, let us write 2 1 plus 0 into 2 plus 1 times minus 2. Okay. So if they are actually orthogonal, then I call it a, if the column vectors are orthogonal of a matrix, then we call it orthogonal matrix. Or in other words, for orthogonal matrix, this relation will satisfy. This is orthogonal matrix. A matrix will be called orthogonal if we have A transpose or A transpose A equals to I. So for orthogonal matrix, these properties will hold. So 2 times 1. So this is 2 plus 0 minus 2 again 0. Similarly, you can check that x2 dot x3 will also be 0. Okay. Now what we want to create a matrix whose length will be 1. Not a matrix, matrix length not 1, the norm. This is actually, if you talk about two variable case, when we have V is a vector, xi plus yj, then we call this the modulus, the length or the magnitude of the vector is root over x square plus y square. But if we have 3 variable also, or z k, then we call it the length of the vector. Then we take this magnitude of the length of the matrix, we can call it. But when we have higher dimension, this is, you can call it a length. Okay, 2 dimension, 3 dimension, you can call it a length. But if you go to higher dimension, we call length as a norm. Okay, and is denoted by the symbol is this. Or you can write. Okay, so this is a generalized notation, and we will use this notation here in order to find out the length of the vectors, because we want to make it unit. Okay, so if you do this, so we define alpha 1 and then alpha 2 and then alpha 3 by these relations. So x1 divided by the norm of the vector. So this is 1 by root 5, and then into x1. If you just do this simplify, just a simple simplification, do it for all the vectors, and then you will get the, now if you define p equals to alpha 1, alpha 2, alpha 3, then this vector will be actually orthogonal matrix. Not only orthogonal, it is actually, there is another definition called orthonormal. Orthogonal or orthonormal real matrix. Whose rows are orthonormal vectors. In fact, there is another remark. This matrix is also sometimes called orthonormal, orthogonal and orthonormal, if this relation holds, because orthonormal vectors are uh, perpendicular vectors having the length 1. For matrix, we will call orthonormal or orthogonal. Okay. Definition: orthonormal vectors. Orthonormal vectors. V1 and V2 are uh, called orthonormal if V1 is perpendicular to V2 and norm of V1 equals to norm of V2 equals to 1. That means they are unit vectors. Okay. So with this definition, this matrix is also actually keeping the similarity. This matrix is renamed as this vector, orthonormal or orthogonal vector. Okay. Now, if you do, multiply this, so this is going to be 2 by root 5, and you can write 0, 1 by root 5, and then minus 2 by 3 root 5, then 5 by 3 root 5, and then 4 by 3 root 5. Similarly, 1 by 3, 2 by 3, and minus 2 by 3. Now, I am just writing it as a column. If you write it as a row also, then you will get the same matrix, because here you will get P equals to P transpose. If you do the P transpose, what you will get? So 2 root 5, 0, 1 by root 5. So this is actually 3 root 5, 5 by 3 root 5, and then 4 by 3 root 5. Similarly, we have this is 1 by 3, 2 by 3, minus 2 by 3. So let us not write P. So this is, we don't know whether this is a model matrix or some other different matrix. Because if you remember, P matrix, what we have done, that was the eigenvectors. We don't know whether they are eigenvectors or not. So let us not write directly P. Okay. We may write, because this is a matrix. Okay, so Oh no, there was nothing mentioned as a matrix. This was just some vectors. So aim is to find a orthogonal matrix. So we have seen these vectors are orthogonal and we are making their length as a unit. We have defined it. So let us call it a A. And if you write it A transpose, then we can claim that A is an orthogonal matrix. In fact, if it is A orthogonal, then we have seen A transpose equals to A transpose A. It will be I. Easy to verify. So if you may take it as an exercise. Verify these relations also now. If you just multiply them, then you will get this. Okay. Now there is a theorem which says that if we have a real symmetric matrix, and all the eigenvalues are distinct, then their corresponding eigenvectors will be mutually pairwise orthogonal. Here we had only arbitrary three vectors. We don't know whether they are eigenvectors of some matrix or not. Okay, but we will be interested in symmetric matrix because symmetric matrix will be it has many real life applications. I will mention some of them. Okay, the thing is, it has a beautiful property. Suppose there is a question. Try to find out a pairwise mutually orthogonal vectors. So what you can say, if you know this theorem, then you can directly get a real matrix, a real symmetric matrix in such a way that their eigenvectors are mutually orthogonal. It is a given theorem. Only thing you have to make a matrix. For example, if you want to make a particular symmetric matrix, for example, 1 0 0 0 1 0. This is one identity matrix. So this is a trivial case. This is also a symmetric matrix, but the eigenvectors are not distinct here. Okay, so if you can make distinct eigenvectors, distinct eigenvalues, then so here the eigenvalues will be 1 2 3, all are distinct. The vectors that you will get, they are actually orthogonally mutually orthogonal. Not necessary they are okay, the length of this actually unit. So you can if you want to make the length as a unit, then you have to divide by 1 by root 2 or 1 by root 3 maybe in this form. Okay, so this theorem can be used to find out orthogonal vectors. Now what is meant by orthogonal diagonalization of a square matrix? Remember, if P inverse AP, so that is our aim. If this is a diagonal matrix, then this transformation is called orthogonal diagonalization. So in that particular case, this P matrix will be a this matrix P matrix will be an orthogonal matrix. So between this definition and this theorem, it says that if we have a symmetric matrix means A equals to A transpose, real symmetric matrix, and its eigenvalues are distinct. If we have such situation, then the matrix that we model matrix is actually going to be an orthogonal matrix. And if we have this transformation, then this transformation will be called as orthogonal diagonalization, because we are getting a diagonal matrix. So orthogonal diagonalization is only possible for symmetric matrix, real symmetric matrix. So that is also the next theorem. It says, it guarantees the theorem that if A is a square matrix is orthogonally diagonalizable, then A will be symmetric. So this is just a simple proof. I would like to tell you to verify it. And then there are two remarks that no
Sir,
other matrix.
previous slide.
Yes,
Previous slide. Previous one. Okay, sir. Okay.
okay.
Thank you, sir.
Okay, right. So this remark says that no matrix except the symmetric matrix can be orthogonally diagonalizable. Okay. This also ensures that a set of linearly independent eigenvectors of a symmetric matrix corresponds to a set of orthogonal vectors. Okay. So that is, I mean, this is real symmetric matrix. It has some beautiful features. If the eigenvalues are distinct, then the eigenvectors will be orthogonal also. Okay. So this is one example. Try to verify. The eigenvalues of this matrix are 1, 1, and 10. And the particular eigenvalues for this particular eigenvalue, eigenvector is this one. It will have, since 1 has to multiplicity 2, so it may have maximum of 2 independent eigenvectors. So here x1 and x2 are found. Okay. Okay. And then for lambda equals to 10, we'll have this eigenvector. Now, if you try to verify this 2, okay, whether this x1 dot x2 equals to x2 dot x3 equals to x3 dot x1, whether this is 0, verify.
Yes, sir.
In fact, they are 0. So they are orthogonal. But you have to make it the unit. So let us take the norm. Norms means the magnitude or the distance, you can say. How much distance is it visiting? Okay. Length of the vectors is the norm. Once you find them, okay, you define alpha 1, alpha 2, and alpha 3 as the unit vectors, not necessarily I, j, k. They are just some different unit vectors. So this norm will be now this norm of alpha 1 equals to 1. The norm of alpha 2 will be 1, and norm of alpha 3 will be 1. Now, if you form a matrix with this vectors, with these 3 vectors, then it will be an orthogonal matrix. So let us call this matrix as P matrix. Earlier we have seen that we call it a model matrix because all these vectors, the column vectors, are actually what we have seen. This column vectors we have seen as eigenvectors, orthogonal, or let us write orthonormal. Orthonormal eigenvectors. Since this is a P transpose, so you don't need to worry about the P inverse. If you just do it the transpose, then you will get the P inverse. So there is one special, you can say, special characteristic of this type of matrices. You can directly find the inverse, just taking the transpose. Okay. Now it is an easy task to verify. That this P transpose P inverse AP will be the diagonal matrix. Okay. So with this problem, this diagonalization of a matrix comes to an end. There are two tasks I am attaching. Okay, so try to verify them also, whether these results are correct. Okay. Now there is the next topic, which is called this. Let me show this particular actually how I have mentioned that how do we actually use this diagonalization process, and how to actually use in real life applications. So let me just quickly show you two examples. So this is regarding the eigenvalue decomposition for nowadays we use QR decomposition. I mean QR code and all other things. Whenever you do QR payment or UPI payment, you just scan the QR code. Okay. And you will be amazed to know that there is a very close relation between the eigenvalues, eigenvectors, and this QR code. Suppose you have a QR code of this form, this blue, yellow, and some other colors. So normally QR code will look like of this form. It is in black and white or some other case. So if you go back and check the matrix, okay, what happens? You can see that this is actually changing. Okay, but if you look at that, the principal diagonal, it is actually remaining almost the same actually. Okay, this. Okay, here you can see the changes.
Sir, are you presenting?
Yeah, it is not visible.
Yes, not visible.
Okay, let me just. Okay. Just a minute. I will. Is it visible now?
Yes, sir,
Yes,
visible.
Okay, so let us go back and check. So, for example, if you see this as a QR code, although it has a color yellow, blue, and all other colors up there, but if you try to diagonalize it, if you try to, for example, if you think this is a main diagonal as the blue light blue and dark navy blue is all the colors are there. Then you look at the next matrix, which is actually it is you may think that this is a Gaussian elimination, but it is not like that. But you can think of this form. Okay. So here the eigenvalues and eigenvectors, if you remember, not all vectors are eigenvectors. There are some particular vectors which can be treated as eigenvectors if they satisfy some basic properties. Okay. So here you will get of this form. So QR code, if you look at the QR code of your matrix, maybe if you use the Paytm QR code or other QR code, it will change second to second. After a few time, it will change its orientation. Okay. So this is for your information, just that eigenvalues can be taken, elements of the real eigenvalues are taken as inputs. And then we'll compute the all other things. And for at a given time, the QR code will be unique. Okay, so this is one example. There is another example of some beautiful application. Let me just. But this is a much more higher level. Okay. Normally, we recommend this is for PhD scholars, those who do PhD. So, in fact, just to mention that there are applications of yeah. So here it is. If you look at the QR code of this firm, yeah, then so QR code will be this principal component association. For example, if you want to generate this type of QR code, then you have to analyze the vectors that is inside this. Here it is. So principal component, this is a PCA, it is actually principal component analysis. So if you have a data, for example, you can consider the vectors inside the dot points. Okay? You can analyze the principal component, and then you only take those data which are actually they can be treated as a eigenvectors. So this is much more complicated and higher level of study, but for your information, that we can find beautiful applications of this eigenvalue, eigenvector, and diagonalization process. Okay. Now the next topic that we are going to discuss is called quadratic forms, which is also related to eigenvalue, eigenvectors also. Okay. And you can find this QR code or other applications. They are also related to this quadratic forms. So what is a quadratic form? So let us define. A quadratic form are defined as a homogeneous polynomial of second degree in any number of variable. So if you have this is a quadratic form in two variable form, ax square plus 2 into h xy plus b y square. See, homogeneous polynomial. So degree of each variables for each component, each term will have the degree is 2. Here is also 1 plus 1 is 2. Here is also 2. Okay. Now if we have three variable, then we will have of this form. So three variable in quadratic form of this form. And then if we have a four variable case, then we can write of this form. Okay. This quadratic forms, and then this is n variables. So this can be written as of this form. And if you this so quadratic form are actually homogeneous polynomials of second degree. Now these are also will be helpful. So if you call it find the minimum or maximum of q x comma y. So when we will discuss calculus portion, then you will find that these quadratic forms are also useful there. Now, in order to study the quadratic form, our main goal is to, from the given quadratic form, we want to find out the canonical form. By some transformation. So what is a canonical form? Canonical form is actually it will contain only square terms. For example, a1 dashed or a dashed x square plus b dashed y square. So if it is having three variable, then it will be a dash square plus b dash y square plus c dash z square. That means here this xy variables, the mixed variables, okay, the mixed variable quantity will be actually removed. So by some transformation. So how does this actually related to the core? What is it called? Yeah, eigenvalues and the previous topic also. It is also related to the symmetric matrix also. And yeah, so these are called actually sum of squares form. It has some other name. It is also known as sum of squares form, the canonical form. Also known as AKA. Also known as. Okay. Now let us see some example. And how do we actually try to find out? The matrix of this quadratic form, remember that the matrix A corresponding to the quadratic form is actually calculated of this form. So the coefficient of x square. So if you take one example parallelly, so what happens? So coefficient is 1 here. So let us write 1. Then half of the coefficient of xy. So what you do, you write here x, y, and z, and then x, y, and z. So x into x square. So write down the coefficient of x square. X into y. So half of the coefficient of the. So here it is x1, x2. So let us write x1, x2 here. Okay. x1 and x2. x1, x2, x3. Here it is x1, x2, and x3. So half of the x1, x2. So coefficient is 2. So half of 2 is 1. So let us put 1 here. Then x1, x3. So half of the coefficient of 3. So this is 3 by 2. So let us write 3 by 2. Okay. And similarly, this is x3, x1. So we will not differentiate x1 and x3. when their variables will not differentiate as, so they are actually equal. Okay. X3 and X1, we'll consider them as equal. So that is why their coefficient will be 3 by t here. Similarly, uh, we'll take the entry that coefficient, the matrix of the quadratic form will be of this form. So by the nature of this matrix is actually a symmetric matrix. So this is the way, but remember, Q is not equals to A. Q is the quadratic form. It is a scalar value. Scalar quantity. But this is a matrix. So this is for your information. That now, once we find it, so you can go back. Given the matrix, suppose the matrix is given. Task is to find the quadratic form. Find the quadratic form. So what we will do, we will actually take x as a variable, x1, x2, and x3. Then q x1, x2, and x3 will be called a quadratic form if we have x transpose A, x is a quadratic form. Where A matrix is given. Our target is to find out this quadratic form, this scalar quantity. So for that, what we'll do? We'll multiply with x transpose A times x. So this will give you the function. Okay, the functional value is this one. So given a quadratic form, we can find a matrix. From that given a matrix, if it is mentioned that write down the quadratic form for the given matrix, so the associated matrix, from the associated matrix we can find out the quadratic form. In fact, this matrix is very important when we'll discuss the maxima and minima. Now it is time to discuss about the concepts, that is, okay, so there is another concept called how to relate the quadratic forms and eigenvalues and eigenvectors. Now for quadratic form, you know that if q x1, x2, and x3 is given, then we can find the matrix. And we have seen that this matrix is nothing, is a always symmetric matrix. But for symmetric matrix, we have seen that if we have distinct eigenvectors x1, x2, x3 are distinct, then what we get? The P matrix composed of x1, x2, the eigenvectors are x3, then this is going to be orthogonal matrix. And if we have P inverse AP, we'll get a diagonal matrix for where we have lambda 1, lambda 2, and lambda 3 as the diagonal entries. So with this relation, we'll try to look at the sum of squares form. Okay. Okay, so this is arbitrary matrix. We are taking one symmetric matrix. So if you take that A, H, G, then A, B, C, we have to take as a diagonal elements, and we are making one symmetric matrix. And then what we take, if you take this corresponding eigenvectors, linearly eigenvectors for a particular matrix, then this is going to be the eigenvectors will be the three elements of this eigenvector, that is, so the sum of squares will be, because if you remember, the P inverse AP will be a diagonal matrix. Okay, and the diagonal will be lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3. So if you take it here, x1, x2, and x3, and here also if you write x1, x2, and x3. Now if you write down if this is the matrix of the quadratic form, then what will happen? If you write down from a given matrix, if you try to write down the quadratic form, then this will become lambda 1 x1 square plus lambda 2 x2 square plus lambda 3 x3 square. So only the square terms will be there. All other terms will be removed. Okay. So this is how we relate the quadratic form, a matrix of a quadratic form, and we try to find the canonical form. So from the diagonalizability theory, we know that P inverse AP is equals to D. Now if you just multiply this P matrix as of this form, then you will get that this form is known as the canonical form. Okay. And this P matrix is called matrix of transformation, which is an orthogonal matrix, because we are if you verify this matrix, if you verify whether they are perpendicular to each other or not, then you will check that they are actually perpendicular, because these matrices, these vectors are eigenvectors of a symmetric matrix, also known as sum of squares form, or it has another name, is called the principal axis form. So this is actually related. You can relate this quantity in the QR code also. Like if you have some kind of data, these data are given. Okay. Now, if you have the lambda values, the eigenvalues, if you know them, okay. So from here, you will take these vectors. Which one is going to be which one? Which vectors are in the actually principal axis? So there, you will get which vectors are holding this property Ax equals to lambda x. Okay. This eigenvalues and this particular eigenvectors, because they have special properties, they will be scaled keeping the direction same, keeping the line of direction same actually, not the direction, because if it is negative, then you will get this direction. If it is positive, then it will get this. But this vector will not change its line of, it can be scaled in the same direction or in the opposite direction. Okay, so that is why whenever you want to study the principal component analysis, if you have a data of this form, if you want to study them, so this principal component analysis is very related to this form also, because this quadratic form will have sum of squares as the. Okay. Now this particular transformation is called congruent transformation, or it is also known as orthogonal transformation. That if you make it that from the quadratic form, you get the canonical form. Okay, and this transformation is called congruent transformation or orthogonal transformation, because the matrix that you get is actually orthogonal matrix. Now, if you look at that one example, so this is actually 3 x square plus, suppose the QF u is given as this form, 3x square plus 5y square plus 3z square minus 2yz plus 2zx minus 2xy. So if you have this problem, then find the matrix, the associated matrix. The matrix of the QF, okay, the quadratic form. Is given by A. So let us write. So this is x, y, z, then x, y, z. You have here 3, y square equals to 5, and then z equals to, again, it is 3 is given. Okay. Now, for xy, it is minus 2xy. So this is half of minus 2, then this is also half of minus 2. Similarly, you think about xz. So xz is plus 2. So half of 2, here also half of 2. Now you consider about the yz. So this is yz. So half of minus 2, then half of minus 2. And the matrix becomes now 3, minus 1, 1. So minus 1, 5, minus 1. And then half is becomes 1, minus 1, and then 3 is a symmetric matrix. Now if you try to find out the eigenvalue and eigenvectors, then what you will get? Find the eigenvalues of A equals to, here it is 3, minus 1, 1, minus 1, 5, minus 1. So 1, 1, minus 1, 3. Okay. So you will get lambda 1 equals to 2, lambda 2, verify, lambda 2 equals to 3, and lambda 3 equals to 6. Okay. Because if you do this determinant, that is A minus lambda I equals to 0, and solve, so you will get these values. So the canonical form, you can directly write, because this is a symmetric matrix, the eigenvector and the eigenvalues are actually distinct. Okay. So by the previous theorem that we have discussed earlier today, that there's eigenvectors x1, x2, and x3 eigenvectors will be orthogonal. Not only orthogonal, we can make them orthonormal also. That means length of the vectors will be 1, non-normal, orthonormal. Okay. So for that, if you write P matrix, P inverse, if you write P as this matrix x1, x2, and x3, then you write P inverse, you find P inverse AP will be nothing but, this is a diagonal matrix, 2, 0, 0, 0, 3, 0, and 0, 0, 6. So from here you can take the canonical form. So that's an easy task. You can verify that the canonical form is given by 2x square plus 3y square plus 6z square. So this is our canonical form. What was our QF? QF was given. Okay. So QF was 3x square plus 5y or 3x square plus 5y square plus 3z square minus 2yz plus 2zx minus 2xy. So this quadratic form is actually transformed into by the canonical form. Okay, with the help of eigenvalues. Now there are some more examples for your practice. So if we have, so this is reduce the canonical, this is the quadratic form. Reduce this quadratic form into its canonical form. Okay, and discuss the nature of Q. So nature of the quadratic form, that we will discuss it in the next class. What is the nature? Any doubt so far regarding today's class?
No, sir.